introduce Enno Kessler and for his talks, and we'll talk about super stable maps of genus 0.
Thank you for the introduction, and thank you to all of the organizers for the invitation to come here and to speak. So I want to report on this long-going project on super stable maps or generalizations of J-holomorphic curves and stable maps to the case where the domain is a super Riemann surface and the target is a classical almost Kessler manifold. And as what I just said already hinted at the fact that I'm looking at all the things more from the symplectic or differential geometric perspective. So we need to talk about generalizations of J-holomorphic curves or pseudo-holomorphic curves first. So super J-holomorphic curves. So definition. A map phi from a super Riemann surface M to a non-super almost Kessler manifold N with symplectic form omega and compatible almost complex structure J is a super J holomorphic curve if dj bar phi vanishes. So, and dj bar phi is the operator that maps phi to the anti-holomorphic part of the differential restricted to this distribution D that sits in the definition of super Riemann surface. So let me recall super Riemann surfaces. Definition was in Nadia's talk already, but I will write it down. So a super Riemann surface is a complex one-dimensional supermanifold together with a distribution D in the tangent bundle such that the commutator induces an isomorphism from D tensor D to Tm modulo D. And we will assume closed and compact for the moment. Okay. So, as we might have seen in Nadia's talk, this seems to be the right supergeometric generalization of Riemann surface or algebraic curve to the world of supergeometry, with this extra thing that there is a, even though it's 1/1 dimensional, behaves like curves in many aspects due to this distribution D. So the moduli theory has many similarities to the moduli theory of algebraic curves and so on and so on. And so the idea that we have is now to look at the next step and to look at generalizations of maps that satisfy maps out of super Riemann surfaces that satisfy good holomorphicity properties. So what is the motivation that we have to study this? Yeah, first, I mean, it's a generalization of pseudo or J-holomorphic curves and stable maps later. To superworld. And this includes the dreams of generalizations of Gromov-Witten invariants to the superworld that I will say a few comments at the end about. And then where I came from to study this equation is that solutions to these equations are actually critical points of an action which is written in the super geometric language as follows. So I integrate over my super Riemann surface the differential of phi norm squared restricted to D with respect to some volume form, Berezinian volume form, which is the right generalization of harmonic maps. And like classical J-holomorphic curves are absolute minimizers of the Dirichlet action. These maps that satisfy this equation will be critical points of this action, which can be seen as the correct generalization of harmonic or Dirichlet action to super Riemann surfaces. And I've studied that before quite a bit. So by constructing spaces of solutions to this equation, we also construct spaces of solution or critical points to that. Well, I said some volume Berezinian form. I don't really want to explain what that means, but yeah, okay. Okay. And there's one more point. So if n is actually Kessler and not almost Kessler, that is, this J is actually coming from is integrable, and it's coming from an integrable almost complex structure, then phi is holomorphic. So that is also very plausible because that is something that you expect from J-holomorphic curves. Also, if you have a J-holomorphic curve from a classical Riemann surface into a complex manifold, you want that map to be holomorphic. And it's not straightforward here because we don't check that the anti-holomorphic part of the entire differential vanishes. We do that only on D. But that is also a phenomenon that is known for a long time, that somehow holomorphicity of functions on super Riemann surfaces can be checked by checking it on the D-line bundle only. Sorry, what? This says 1 plus I. I is the almost complex structure here. J is the almost complex structure on the target. Differential of phi restricted to the D-line bundle. That, yes, that's a tensor product. So it is, take the anti-holomorphic part of the differential and restrict it to the D bundle. Rank. 0/1, so it's odd. Yeah. Okay. And so I want to write down examples, explicit as possible. And first for super Riemann surfaces. So C11 with standard coordinates Z and theta. Then we can define this distribution D as the one that is generated by d theta plus theta dz. And how is this satisfying the definition? Well, you can actually check that, if you call this thing D, that the commutator of D with itself is, due to the signs that we are using, 2 times dd. And then if you apply D to itself, you see that the d theta here kills that theta. So you get 2 times dz, which is in the complement of D in Tm. So this is the local example, the only one. And the next, more interesting, because I said closed and compact, is P11. P11 is the generalization of the Riemann sphere, and it has two local charts. Z1, theta 1, and Z1, theta 2. And it has the gluing functions that Z2 is minus 1 over Z1, and theta 2 is minus theta 1 over Z1. Is that correct? Yes. So this the signs look strange at the beginning, but it's relevant to see that that this vector field transforms correctly. Okay, so now let's look at an example of a map from C11 to Cn, and we take on Cn coordinates yj, and then I can express my map phi via coordinate functions. That is, I need to say how it acts on the coordinate functions phi yj, and I will write it like this. That's theta. So this is, I can expand with respect to the coordinates, I mean the odd generators with the odd coordinates here, and the remaining coefficient functions like this one here, that's actually a function of z and z bar, right? We're not starting with holomorphic maps, we're starting with smooth maps, which I can express in the coordinates z bar, z bar, theta, theta bar. And now I want to evaluate the equation that we had at the beginning. Del J bar phi is given by, well, del theta bar plus theta bar del z bar applied to phi sharp j times, well, so that is the differential, and we need to take this derivative and see what happens. Everybody can start doing that on their own paper. And what I got is psi bar minus theta, so j, fj 1/2 plus theta bar del z bar phi j minus theta bar del z bar psi j times phi upper star. So, and if we want this thing to vanish, which is the original condition, all the coefficient functions here need to vanish. That is, psi bar needs to be 0, f needs to be 0, dz bar of all phi j's needs to be 0, and dz bar of all psi's needs to be 0. And this is in line with what I said earlier, that we expect the map to be holomorphic if the target is holomorphic. No. This? Okay. Thanks. Okay. Good. So now to simplify what I'm going to say in the following, let's make a big assumption. So the domain super Riemann surface is P11. That is, we do genus 0 only. And by uniformization of super Riemann surfaces, it is known that P11 is the only super Riemann surface of genus 0. And the target is Pn, complex projective space. So all of the statements that I'm going to say have more general versions, but I will not bother stating the precise conditions on every theorem. If you care, please ask. But all that I'm going to say works in those examples. And it is mostly harder to get rid of this condition than this condition. Okay. So the first thing that I want to do now is to show that this, what we see in here, that I can express this super PDE from here in terms of component fields, that this also works more generally. So there is a standard map I from P1 into P11. And I mean, we see what we expect it to be like, right? It is the map that then sends Z, I mean, that sets thetas to 0. Right? So it's theta is equal to 0, and I upper sharp Z is Z. Okay, so that's a holomorphic embedding in this case. And we can then define the following things. We can define little phi as being capital phi composed with I. So this is a map, first I, from P1 into P11, and then into our target. Then we can define a thing psi, which is the restriction of the differential of phi to D and pulled back along I. And this is a smooth section of a twisted spinor bundle. So here, my vector bundle S is O of 1. And that's actually the same thing as I upper star D from here. So this psi is a smooth section of dual spinor bundle times tensor phi upper star Tn. So it is a twisted spinor. It depends both on the spinor bundle on the domain and on the target tangent. And when then there is a map F, which I will not entirely explain. So there is a second order odd differential operator applied to phi. And you should think of this in good local coordinate as being dd bar, which fits with the local calculation that we did up there. The F is the coefficient of theta theta bar. Okay. Good. So then this equation dj bar phi equal to 0 is actually equivalent to the following set of equations, which we have mostly proven. Del j bar phi equal to 0. Some twisted Dirac operator applied to psi is equal to 0. 1/2 of 1 plus I tensor j times psi is equal to 0. And F is equal to 0. So this is the global version of what we have proven up there. Okay, comment. So this is the classical equation for J holomorphic curves in the setting of symplectic geometry. So what we have done really extends and contains the classical theory, because we could set psi equal to 0 and get back the classical theory. Those two equations together tell me that psi is actually a holomorphic section of the complex tensor product, so complex twisted spinors and holomorphic section. So this is, the anti-holomorphic part vanishes, and this can be written as a holomorphicity constraint as we did up there. So we have reduced our original equation that is still here, which is entirely PDE on super side, to something that is more classical. It depends on Z, not on thetas anymore. So we can hope to apply some more classical PDE theory and say something about the solution space. And this is what we will do now. So there is a big theory around this equation, which I have learned mostly from the book of McDuff and Salomon, where they show how to construct a moduli space of solutions for this equation. And in the article that I've mentioned at the beginning, we have generalized this to these coupled equations. Okay, so it follows the moduli space of super J holomorphic curves is a supermanifold of dimension 2n, so this is a real dimension 2n plus first Chern class of the target. Here's something missing, such that I reduced image. Sorry, one needs to fix the image of, the image of the map, of the reduced map in the homology of the target. So, and this is what I call A. So 2 times. So the moduli space of super J holomorphic curves is a supermanifold of dimension 2n. N is the n that we had everywhere, dimension of the target, and plus first Chern class of the target applied to A, and odd dimension 2 times first Chern class of the target applied to A. Okay. This part of the theorem is basically proven using PDE methods. One constructs the infinite dimensional supermanifold of all maps phi, a certain vector bundle over it, such that the operator is a section, and then you apply, up to analytical technical details, you apply an implicit function theorem to obtain local charts for your moduli problem. So I will not go into the details here. I want to go more into the structure of this moduli space. And here's, so then, a more recent result. Moreover, the reduced points, so I call this moduli space Sm of A. So the reduced points of this moduli space Sm of A is the classical moduli space of J holomorphic curves with fixed domain into that target, and the supermoduli space of super J holomorphic curves is a split supermanifold. This is smooth split. Of the normal bundle of the embedding of the supermoduli space, well, the embedding of the classical moduli space into the supermoduli space, and this vector bundle NA can be described explicitly. This, yes. So this normal bundle of the supermoduli space has at a map phi, well, little phi. It has the fibers H0 of S dual tensor phi upper star Tn. So this is something that we had expected already when seeing here. The supermoduli space that we're constructing consists of pairs phi and psi's. Psi is holomorphic. And so somehow the more recent insight here is that this construction with the implicit function theorem gives me an explicit smooth atlas that is split, that is satisfying linearity conditions on the patching data. Well, this is a smooth moduli space. It's not. I didn't say anything about complex yet. I mean, it's smooth, differentiable smooth. It's not holomorphic. I didn't say that neither, but I didn't explain anything about the J holomorphic about the structure. So I will. Okay, sorry. So if the target is scalar, you can pull back the J to the moduli space, right? The tangent. Sorry. So it's not. So how to say that? If you linearize this equation, if you linearize this operator, you get that the tangent space to the moduli space is the kernel of the linearized version of this. And the kernel sits inside smooth sections of the pullback tangent bundle. For fixed target, yes. And this obviously has an almost complex structure. J, we used it all over the place. So also the pullback has this almost complex structure. And what you then need to see is that this, if the target is scalar, that this kernel preserves that almost complex structure, and that the almost complex structure is integrable. So in this very last step, the integrability, I'm not aware how that works. So it is in the book by McDuff and Salomon, they just write for the classical case, it is obvious the following is integrable. And I've gone around and asked people, can you please explain how this is obvious? I don't understand it, but I expect that when somebody comes and explains why it is obvious, it will just work the same way for super. So I can explain if the target is scalar. I can explain how I get an almost complex structure on this moduli space, but I don't know why it's integrable, but I expect it to be integrable. The target, I don't deform n for the moment. I have not done that for the moment, no. Okay. So, yeah, now we want to get closer to what you're maybe thinking about. So we want to look at stable maps. And the idea of stable maps is the following. Up from now on, we have fixed our P11 and mapped it into a larger space. And we have not cared particularly about what happens when I rotate this, how many symmetries do I have? I have kept the domain fixed. So as it, well, you can see it on the picture, it's very symmetric. There's many isometries. And so what you do, you add marked points in order to avoid it, that this has automorphisms. And what you end up with is then the following. Consider tuples Z1 up to Zk and a map phi. So these are points of P11. And as we are doing supergeometry, we know that points is not enough. We might need some extra odd parameters. So we need B points of P11. And this is a map phi. So we consider tuples of marked points together with maps, as I've tried to draw here. And we say this is equivalent to G of Z1 up to G of Zk, comma, phi compose G inverse for G, a superconformal automorphism of P11. So the automorphisms of the super Riemann surface that we need to consider. Okay, so, and in addition, I want those marked points such that their reductions are distinct. Okay. So such a tuple will be called a stable map for the moment. There is more general stable maps though. Okay, so moduli spaces of such tuples is then the following. We will call it M0K of A, sorry, S. And it is something like the ZKs times the moduli space that we have constructed before, divided by superconformal automorphisms of P11. So, and this thing is a superorbifold. Yes, so that Zk is the submanifold, super submanifold of P11 to the K, such that the reduced diagonal is not in there, right? I need to take out all those points where the reduced points coincide. I mean, all the tuples where two of the reduced points coincide. Sorry? I need to take out all those where the reduced points, I mean, where in the tuple of K reduced points, two of them might coincide. So I need to take out certain diagonals. Yes. Yeah, it's not compact yet. I mean, there's no bars here. Okay. So I will not really explain what I mean by this superorbifold. I would rather do something very similar to what we did before, and I will explain the reduced points of this thing. And the first order, like the normal bundle, the first order odd directions. So this is to be thought of as the reduced points of the superorbifold and the normal, like the normal bundle that we were considering before. Okay, so in order to evaluate, I mean, I have explained this, more or less. I have explained this, more or less. What is still missing is what is this automorphism group that we need to consider. And it turns out you can go read the literature. You can, for example, read the book by Manin, or there is also a paper that is a bit more explicit by Rita Fioresi and Stephen Kwok, which tells you the following. If you take like projective coordinates on P11, then you can multiply, I mean, you write it as a column, and you can multiply a matrix. So if this is in GL C2, you get a holomorphic automorphism of P11. But you don't only want a holomorphic automorphism, you want something that even in addition preserves the holomorphic distribution D. In order to preserve D, one needs that AD minus BC minus gamma delta is equal to 1. One needs E squared plus 2 times alpha beta is equal to 1. One needs C alpha minus A beta is equal to E times gamma, and D alpha minus B beta is equal to E times delta. So in those equations define something which is usually called OSP 2,1 inside of GL 2 slash 1. What did we do? Huh? Sorry, 1 second. Now you. If you're clever, yes. If not, it gets long. So basically, what you need to do is, okay, it's in my book. Go read. But you can also find it in Manin's book before me. Yeah.
So interrupt you. What is
A? A is that homology class.
Okay.
That we needed to fix, because the dimension depends on that homology class, and you want a moduli space with fixed dimension. You don't want you don't want the moduli space to be different. A union of manifolds of different dimension. Yep. Okay. Good. And but there is these equations here that preserves D, but now there is still, as you know from classical projective space, if you multiply this matrix by some factor, it will not change. So you need to go to something like the projective version of PGL, and you need to satisfy this. So the superconformal automorphisms of P11 is actually OSP21 divided by Z2, because the Z2 is the only thing that remains from the rescalings, because you have certain things fixing ones here. Okay, and we will indeed realize this. We will embed this into OSP21 with the condition that E reduced is +1. So if you look at this equation, you see that it has two components. The E reduced could be plus or minus 1, and we take the part where it's +1. Okay, so next up, let's look at, sorry? So first I said we need to consider this quotient, because if I rescale by, if I multiply all this thing by -1, it goes here to -1, so that's the same map. Then I said I want to realize this quotient as sitting in OSP21 as the component where the E reduced is +1. Look at this equation. This equation says the reduced part of E, this is two odd things, is either plus or -1, and I only want to take the part where E is +1.
So that's the component and the derivative changes.
Yes. But this is a non-canonical choice, and this is still canonical somehow. Okay. Right, that, yeah, okay, in that sense it's more gonna, yeah. So first thing is that, well, SL of 2 sits in SC of P11 by mapping this matrix A, C, B, D to the matrix A, C, B, D, 0, 0, 1, right, using that choice that we just did. And moreover, so if you take the entire reduced points of P of the automorphism group, that is precisely SL2, right? Because here we have odd functions. If I do only consider the reduced points, those odd functions go away. They need to be 0. So this is true. So what we can learn from this is that the reduced points of this supermoduli space M0K of A is ZK reduced times MA, so it's the reduction of the supermoduli space divided by SL of 2. And this gives you precisely the classical construction of M0K of A, but there is a Z2 isotropy group. So as quotient topological space, this is true, but every point has a Z2 factor, right? Because classical, you would only write PGL2 here and not SL2. And so we have understood that this moduli space of stable maps up there is also extending the classical moduli space of stable maps. So now that we need to look at the R01 points. So if our parameters alpha, beta, and gamma depend on one additional odd parameter. So R01 points of that. And that is that I can write my matrix A, C, B, D, alpha, beta, E, gamma, delta as a matrix A, C, B, D, 1, 0, 0 times 1, 1, alpha, beta, minus beta, alpha, 1. So this is the case that we did before, and this is the new things, right? So this is SL2 again, and this is something that I will call SUSY, and we need to study how this acts on all the things that we are looking at. So on the mark points and on the map. So let's look at it. So if you take Z1, Z2, theta, and multiply this matrix, you get Z1 plus theta alpha, Z2 plus beta, theta beta, and minus beta Z1 plus alpha Z2 plus theta. And if you stare at this long enough, you will see that this, if this is invertible, is the same thing as Z1 plus theta minus beta Z1 plus alpha 1 minus beta Z1 plus alpha plus theta. So we're looking at an automorphism that does not change P1 inside P11, but it moves the odd directions a little bit. And this is why it's called supersymmetry. And I mean, from this, you can already read off what it does on the mark points, right? It moves every mark point by beta Z1 plus alpha. And for the map, it's a bit more tricky. Let's do that now.
Greek letters are odd.
Sorry?
Greek letters are odd.
Greek letters are odd, yes. Sorry. Did not explain that enough here. Okay, good. Well, most of the Greek letters are odd because I'm now going to write an even Greek letter. I'm sorry. So phi is phi plus theta psi from the beginning. So now I need to look at this inverse, right? Phi composed G minus 1. And what we get is that this is phi of Z plus theta minus beta Z minus alpha plus beta Z plus alpha plus theta psi. And so if you know, if you plug in an odd variable into an even function, you need to take some derivative. So what you get here is phi of Z plus theta times beta Z minus alpha dz of phi. And all those products here will vanish because we have, every product of odd things will vanish because we have only one additional odd parameter. So plus psi. So this is what we were looking at. Sorry? G is this. Good. So basically we have calculated that the mark points are moved by this, and the map parameter psi is moved like that. And so what we can do is we can write this more geometrically in the following way. Okay, so this beta Z1 plus alpha is a holomorphic section of the spinor bundle that we had at the beginning. And this maps to the normal direction of all the mark points, which is sum of restriction of the S bundle to the points Pi, plus the normal bundle to the supermoduli space that we were looking at the beginning of the J holomorphic curves moduli space. And it sends a section S to the restriction of S to Pi, and it maps psi, it modifies psi by this, this expression here, which can be more invariantly written as minus S contracted with d phi. So how to explain that? So this thing here is a section of cotangent of P1 tensor phi upper star Tn, but we have the property that this is the same as S dual tensor S dual, this. So I can contract it with a spinor. And obtain something that is a twisted spinor as it should be. And then so this is the geometric version of the supersymmetry map that we have studied in the details here. So it is the things that come from up there. And Here? Okay. Yes. So in principle, there should be another term. There is the following. We have all the psi's, alphas, and betas. As we're looking at these, where did I say that? The R01 points, they are all odd, but proportional to a single odd parameter. So whenever I have products of several of those, they need to be 0 right away. So yes, in principle, when you do the more general situation, this entire expression will be more complicated. Sorry, was that for me? Right, we only look at first order odd direction somehow. Okay, good. So what I then want to argue is that this M supermoduli space 0K of A, R01 points, is the R01 points of ZK cross supermoduli space of A. Divided by what? Superconformal automorphism R11. Is the same thing as the co-kernel of this SUSY map. So this is what I explained here, up to the remaining SL2 action, which is the matrices up there that we didn't talk about yet. So one needs to check that this entire construction is SL2 equivariant, and that you can take successive quotient, first by this SUSY part, and then by the SL2 part. And you will see that as long as you have only one of those extra odd parameters, this just works.
Is that just H0?
Huh?
Is that just H0, or is it global section?
Global holomorphic sections, right? I mean, it is expressions of this form, beta z plus alpha. You see how that are global sections of O1. So now, there is the following lemma, which I will not explain, but which I hope I have sufficiently motivated, is that if k is bigger than 3, then M0k of A is C01 cross ZK minus 3 prime cross M of A divided by Z2. So basically, there is a phenomenon that, I mean, we all know that Möbius transformations can be used to fix 3 mark points, and super Möbius transformations can fix 3 super points up to 1 odd parameter. This is the remaining mark points, this is this, and the isotropy that you still have is Z2. And that is the same Z2 isotropy that we have seen earlier, which comes from this SL2 matrix, which is minus the identity. Okay, and I mean, if you look at this, you can also see more easily that this normal bundle, which we have described as this big quotient here, in this case is well, there is the normal direction to the third mark point, which did not get fixed, plus S at the points Pi for I bigger than 3, and plus the normal bundle that we studied at the beginning of the super J holomorphic curves moduli space, and the entire thing divided by Z2. And this is the Z2 that sends all odd directions of the mark points to minus itself and psi to minus psi. Okay, good. So now, So there is more general situations. So if you open up algebraic geometry textbooks, you will see that when they talk about stable maps, they actually want situations where you have copies of P1s glued together like this. And then you will draw trees to classify such things. And what I want to say is, we have understood the situation of one of such bubbles together with the maps, and now we can just glue things together. And I will explain that this does not do a lot. No, sorry, I will not explain it, I will just state it. So if you have a supermoduli space for more complicated, so for a tree T, which arises from, say, connecting two trees like this, and you have a collection of classes, then this is just the same thing as the product of moduli spaces of T prime cohomology classes A prime with the other one. The only condition is that the two marked points here need to lie and have the same image in N. That is one even condition. And as you can read off from the equations at the beginning, one even condition is basically only that the reduced maps need to coincide. So there is no additional condition on the spinners at that point. And that particularly gives you that the moduli, that the normal bundles that we were constructing is just the direct sum of the corresponding normal bundles pulled back to the product. Good. So now, if you give me 5 or 10 minutes, I want to report on the resulting dreams that around supergrammar-Witten invariance. Good? Okay, thank you. So let's make motivation or dream. So what I'm going to say is not proven or published or anything. So dream. So we have constructed many moduli spaces of stable maps. We can construct, we can take the union. We will have something that is like the moduli space of super stable maps and its compactification. So assume we have M0K bar of A in algebraic geometry. So I'm switching to algebraic geometry instead of the symplectic geometry, plus a well-working intersection theory So there is attempts at intersection theory. The papers, not really at intersection theory, but at child groups in Daniel and Ugo's paper at least. But for the moment, this is still a dream, the intersection theory. Plus a torus action on those supermoduli spaces, leaving the classical moduli spaces in them invariant. Plus a torus localization theorem. So I said dream. This is at least 4 dreams. So it's nothing of this is really done. So the last paper that I've done at the beginning, we have studied smooth torus actions on the constituent moduli spaces. So there is something in that direction. but it's not in this generality that I have written it here. In the examples that we have constructed, moduli spaces are split. You rescale the normal bundle, that gives you an action on the split moduli spaces. But this is certainly a thing that is smooth, but it's Gromov continuous. I mean, it's C star, in that sense, complex, but it's not holomorphic. It's differentiable smooth. I mean, so the holomorphic one that we would need for the following is a dream.
What kind of localization?
Yeah, I will write it down in a second. You will see. I mean, the people that do the stable maps business, that means this torus localization, that means something to them. So then what you would want to do is you would want to do super Gromov-Witten invariance of your target, some homology class 0k, of some homology classes of your target, alpha 1 up to alpha k. And it would be natural to write the following. We integrate over our super moduli space, M0k bar of A, the evaluation pullback of alpha 1 up to evaluation pullback alpha k. And here the evaluation maps, that is the map from the moduli spaces that maps to phi of zi, so in the target. So now the torus localization theorem, for if it were working, would give you the following formula. So this is the normal bundle of this dreamed supermoduli space with respect to this one. Okay, so and as it turns out, this last thing, this last formula here, this is something that you can evaluate classically. So up here we have classical forms. Up here, down here, something depends on the normal bundles that we have constructed. And so we can kind of say, dream of, take this formula and run and evaluate it. And now you will have the following objection. I have dreamed all this. Why would this ever be a reasonable definition? And I don't have a very good answer to this, except that this thing, the way that we interpret this formula, it satisfies properties that are generalizations of Kontsevich-Manin axioms. So in particular, what I have just erased, this additivity of the normal bundle yields us a generalization of the gluing axioms, which gives something like super quantum cohomology. And I'm on the way of calculating examples for this. So thank you very much. Yes, I mean, this is super scheme, super stack. We need, I mean, in order to write something like this, or Gromov-Witten classes, you would need some intersection theory for this, right? But I'm not saying I have an idea what this means. I'm just saying if we had in addition this torus action, we would get this. And this is a formula that can be somewhat evaluated classically. And it looks a little bit like guesswork, but it seems to have good properties. Okay, but this. I mean, this is again a classical intersection theory. So, I mean, classical in the sense of what you can read in stable maps books, like the one by Manin or Katz-Cox and so on. Right, I mean, I'm not saying anything about this intermediate step. I mean, if we are very lucky, we do an approximation to that. But I don't know this story. But I'm saying, if we take this formula seriously and see what integrals of this type we can evaluate, you end up with something that seems to have good structure, coming from forgetful maps on superstable maps, something from the normal bundles that I have just explained enter those calculations. So it is this is the normal bundle of the inclusion of the reduced classical stable maps moduli space into the dreamed of super moduli space. And I mean, what I have explained the hour is basically how this normal bundle behaves when restricted to the fixed tree type moduli spaces. So there is certain cases where you can try to evaluate this formula and see what it gives. And in particular, one case that you can do is when A is 0, like the target is only a point. And there is a few more cases that I'm doing at the moment.
And in particular, you did something different from Gromov.
Yes and no. So you need to check what I have written here. The first point is whatever you write here needs to have needs to be a form of the right dimension, right? So if these forms alpha, this evaluation pullback alpha already has the right dimension, that is the dimension of this, this will not contribute. You will get back classical Gromov-Witten invariance. If you violate the classical dimension axiom, so this is called dimension axiom, this property, then some terms from the denominator can show up. Like if this has codimension 1, you will see that the first Chern class of this thing comes up to some torus characters. And so you write something down which depends on the alphas and the first Chern class of the normal bundles. So it contains like first order approximation data of these supermoduli spaces. I will not make claims about this story. There is people thinking about such things, but I don't know. And in the best case, what we are doing is an approximation to that. Maybe it's completely off, but it seems to have good properties. So. I don't know. Sorry. In principle, yes, but I have not thought enough about it. So I know that the small quantum product works for Genus 0 in 3 mark points. I know that. I will not go into generating series for the moment because I have a hard time calculating a few handful of examples. And no.
So yeah, is that if it makes sense to sum over A, sum over the degrees?
Sorry, yes. Well, that's not, as the target is classical, that's not necessarily harder than in the classical case.
Maybe it's the sum over A that satisfies some nice equation.
Yeah, okay. Yeah, the conditions will be more because you have more, somewhere in the when you study the generating functions, you will use that, the degree axioms somewhere. And we violate the degree axioms in places. So there is splittings A equal A1 plus A2 that did not matter before, but do matter now. So all the proof of convergence of these generating series, that will be more complicated. Yeah. Yes. Is that the lemma that you're asking about? So, yeah. Yes. Yeah. SL2. M0k of A super is zk times super MA divided by SC. It acts on both. I mean, you need to compose with the inverse. It acts on like G times Z, phi compose G inverse, right? You want the evaluation map to survive the quotient. So you need this. Right, so the condition is that K is bigger than 3 or A is not 0, right? That's like classical. So this lemma requires K at least 3. Then it gets easier. The construction that I've shown for the normal bundles also works for K equal to 1 and 2. I didn't really consider the K equal to 0 case. So in the preprint that is out now, I have done M01 and M02 explicitly. I mean, a bit more explicitly than what I've shown today. But M00, no, I've not looked at that.
You say that if the degree of the top satisfies the dimension formula, then it takes from the
Mm-hmm.
You look at what happens with maximum environment. That's far from. In other words, you're really doing something like the supervolume.
Yeah.
Did
So I mean, I have looked at the case when the target is a point. I mean, you somehow want the Euler class, right? You get the Euler class of the normal bundle. And if the target is a point anyways, you also get the Euler class, right? Sorry? Because that's one of, I mean, that's one of the few cases that I know of. I mean, it's not, okay, but no, I mean, it gets harder the further I go away from the classical degree axiom. So, yeah. No, I don't think I can say anything insightful right now except, well, I got something.